Okay. You're going to hold one end, and I'm going to hold the other end. Now what I want you to do is look at me, look up at me, and I want you to move that way. You got a little bit of a bend in the rod. Now look back at your rod. Look back at this rod right here. Try and get that straight so it's not too bent. And then come towards me a little bit, tiny bit, a little bit, stop. Okay. Now put a bend in it. Put a bend in it like that. Okay. Good. Now go back to straight. Make it straight. Very good. Now put a bend in it the other way. Okay. Now straighten it out again. Okay. Now I want you to go down. Lower your end. More. Okay, stop right there. Okay, now I want to back out. Let's move this out. Okay. Release.
Now I'm going to show you some demonstration. I am searching object. Now I get object's position. Now I move my arm to approach object. I move my arm to touch target. I close my hand. I move my arm to ready position.
Yeah.
I hand over object to my guest.
You 把手伸过来，拖着手，OK。
I understand that you say prepare walking. Confirm yes or no.
Yes.
Roger.
Prepare walk.
I'm doing it.
Walk forward.
I understand that you say walk forward. Confirm yes or no.
Yes.
Roger. I'm doing it.
Walk backward.
I understand that you say move backward. Confirm yes or no.
Yes.
Roger. I'm doing it. I understand that you say turn right. Confirm yes or no.
Yes.
Roger. I'm doing it.
Stand up. Stand up.
I understand that you say stand up. Confirm yes or no.
Yes.
Roger. I'm doing it.
Detect object.
I understand that you say detect object. Confirm yes or no.
Yes.
What color is the object?
Red.
Detect read object. Confirm yes or no.
Yes.
I can approach the object by following the steps. Turn right 4.64 degrees, move forward 1.45 meters.
Kỳ quan.
There have been many revolutions, and now we're facing the next one, connectivity. But how can a company handle this? What does the industry of the future look like? Our experts have been wrestling with these questions for years. They know that the complete digitalization of the manufacturing industry plays a key role in the process. Why? That's simple. In the future, it will be more important than ever to operate quickly, flexibly, and cost-effectively. Product life cycles are becoming increasingly shorter, while product variants are becoming progressively larger. Just like large volumes, small quantities must be produced economically. Lead times will become shorter, so that delivery must become faster. For companies, this means that in the future, they must align their organization much more rigorously to meet customer needs. This can only be achieved if companies start today to digitize, automate, and above all, interconnect all processes. Not only within the company, but also along the entire value chain. This means a convergence of the various areas. Customers and business partners are part of the total process. The goal is to make all relevant data available anytime and be able to control the whole network of value creation in real time, from product planning and product and production development all the way up to production and logistics. Of course, data security must be assured at all times. Synchronizing digital and physical value streams not only increases productivity of companies, but also their efficiency, quality, and innovative capacity. The Industry 4.0 concept isn't new. But unlike before, we now have the knowledge and technology for it to become affordable reality. As you can see, the industry of the future presents us with many opportunities, challenges and questions. But what's most important? What will you do? Let's shape the future together. Securely, cost-effectively, with quality and efficiency. KP.
I'm ready.
We make no secret of the fact that we are determined to head right to the top of medicine. That's what we're doing. This is a beautiful example of it.
I saw a machine that I'd seen 7 or 8 years ago in a lab building in Germany at Siemens, which was now a reality. And when somebody explained to me how it was going to be used, what more can you say?
We had this vision of what we thought the future of the operating room should be and what the future of surgery should be. And having an administration that was supportive of this future vision, we were able to, with a lot of people's help, create these rooms, which are not only operating rooms that have the state-of-the-art of technology, but operating rooms of the future, where we're going to actually change what surgery is.
We're the first hospital in the country to have 2 of these units in the operating room. Just the whole concept of what is surgery or what is needed to treat diseases is changing. We're going to redefine what a surgical specialist is even, because a surgical specialist now has to be an information technology expert. They have to be a radiologist, endoscopist. They have to be able to do minimally invasive surgery. They got to be able to do conventional surgery.
This revolution is really this merging of intervention with imaging. Imaging equipment that allows us to be better surgeons and allows us to be minimally invasive surgeons.
In this room, at least 12 different image devices so that you can have multiple inputs.
It starts with the electronic medical record. Everyone has access to it. The surgeon has access to it. The anesthesiologist has access to it. The nursing team has access to it. We can communicate with the pathologist upstairs. We have the images from the endoscope, from the microscope. Everything can be viewed at by the clinicians and the people that are taking care of the patient, so we can get everyone's feedback instantaneously.
We're optimizing the patient's care by putting in the hands of the surgeons every conceivable piece of information in the room, helping the physician do the best job for the patient.
And it's not just the surgeon, it's the nursing team, it's the anesthesiologist, it's the whole team.
If you notice attention to detail, where the nurse's station over there is, that desk faces the patient. In all our existing operating rooms, and in most operating rooms around the country, the nurses' desks and the computers are facing the wall. That certainly adds to the patient safety.
You can always accomplish much more when you bring many minds from different disciplines together. I think that's really the exciting thing about being an institution like New York Presbyterian. I mean, we couldn't have done this without the help of donors like the Helmsley Foundation to mobilize the kinds of resources to build this kind of environment. Basically what this machine can do is if you take fluoroscopy and spin it around the patient, you get a three-dimensional image. You can see blood vessels in 3 dimensions. You can see solid tumors in 3 dimensions. You can see bone if you're putting in instrumentation and hardware.
By that spinning motion, you can also create cross-sectional images. What you can start to do now is you can start to say, I'm going to operate on the intestine. This machine will give you simultaneously that intraluminal or inside channel picture, and I'm going to be able to see outside at the same time. And this has the capability that we can overlay those images. So you can start to do what I was saying, Jerry. Think about intestinal surgery where the patient doesn't even have to go to sleep. The average patient nowadays is older, more frail, has more serious accompanying diseases, and so the possibility to eradicate their problem, minimize hospital stay, minimize pain, that's what it's all about, man.
We really want to push the envelope a little bit, and when we start doing that, we don't know where we're going to be able to go with this, and I think that's really the excitement. The excitement is redefining what we're going to be able to do, or from what the standard of what surgery is now, so that with this we can redefine ourselves and really change the way things are done.
And to me, what it represents, not the state of the art, we're ahead of the state of the art.
70% of the world's population will be living in cities covering less than 2% of the Earth's surface. Never have cities been so challenged, and the trend continues to grow. This raises many issues. Pollution, infrastructure access, traffic congestion, mobility, safety, and the health of residents are only a few examples. The development and combination of new technologies, such as the Internet of Things and artificial intelligence, offer a multifaceted solution: the smart city. Smart cities are hyper-connected cities, technologically equipped to improve the lives of their residents. In Mexico, some neighborhoods are still struggling to get permanent access to electricity. So the city installed sensors to analyze the use of electricity in various sectors, so as to optimize energy distribution across the grid. As a result, less frequent power cuts and better distributed energy. In the United Kingdom, the city of Bristol created the Data Dome, a public platform where information on traffic, air quality, noise, or even the city's governance can be shared. They want to grasp the city's pulse by exploiting this data and give local players, citizens, and entrepreneurs the means to build the smart city that truly suits their needs. At AXA, we want to provide our know-how to enable public authorities, businesses, and society as a whole to better anticipate the future, and thereby protect all actors living and creating the cities of tomorrow.
Of leafy greens are growing in huge quantities to be sold to local supermarkets and restaurants. This is Aero Farms, a massive indoor vertical farm in Newark, New Jersey.
Our mission is to build farms in cities all over the world so people have access to fresh, great tasting, highly nutritious food.
Crops are stacked more than 30 feet high inside this 30,000 square foot space. They're grown using aeroponic technology.
Typically in indoor growing, the roots sit in water and one tries to oxygenate the water. Our key inventor realized that if we missed nutrition to the root structure, then the roots have a better oxygenation.
AeroFarm says the root misting system allows them to use 95% less water than a regular field farm. They also use no pesticides or herbicides. Instead of soil, plants are grown in reusable cloth made from recycled plastic. And instead of the sun, there are rows and rows of specialized LED lighting.
A lot of people say, sunless, wait, plants need sun. In fact, the plants don't need yellow spectrum, so we're able to reduce our energy footprint by doing things like reducing certain types of spectrum.
This sophisticated climate-controlled system cuts the growing cycle in half, so crops can be grown all year round, but with a much smaller impact on the environment.
There's all these stresses on our planet. 70% of our freshwater contamination comes from agriculture. About 70% of our freshwater usage goes to agriculture. 1/3 of our arable land has been degraded in the last 40 years. All these macro trends point to the fact that we need a new way to feed our planet.
One of the early champions of vertical farming is Columbia University ecologist Dickson DePommier. In 1999, DePommier and his students proposed that vertical farms could feed overpopulated cities while using less land and less water. They would also cut greenhouse gases by eliminating the need to transport food over long distances. And the idea is finally taking root. Over the past few years, vertical farms have sprouted all over the world, including in Vancouver, Singapore, Panama, the UK, and around the US. Here in Newark, Aero Farms is building out another new farm in a former steel mill, one that's bigger than a football field. Once it's fully operational, it's expected to produce 2 million pounds of greens a year. all grown vertically.
We listen to the plants very carefully to try and understand what they're telling us and try and optimize all these different qualities of a plant. It's a tough business, but it's one that's going to stay and it's going to have a bigger and bigger impact.
Do you think vertical farms will help solve our food production problems? Let us know in the comments below. And check out this next episode to see how
这是带霍尔的五刷电机驱动器，从运行状态来看还算平稳，后期再继续优化。
I am searching the object. Now I get the object's position. Now I move my arm to approach object. I move my arm to touch target. I close my hand. I move my arm to ready position.
Yeah.
I hand the lower object to my guest.
You 把手伸过去，拖着手，
There was a time when the best companies couldn't even consider robots for their production lines.
Welcome to Adept Technology. I would like to introduce you to Adept Technology and to the world of robots, vision systems, and of course to vision-guided robots. Adept Technology is the leader in this industry of small parts assembly and handling with industrial robots. Nearly 50% of the 3,000 installed Adept robot applications use an integrated vision system to ensure quality, flexibility, and a short return on investment. I think you will be surprised to see our robots handling and assembling and inserting parts that you come across in your daily life, like candies, sausages, CDs, and all kinds of consumer products.
Adept Technology offers a complete line of robots that have reach, capacity, and production flexibility similar to manual operators, yet produce the consistent high-quality results of dedicated automation. The Adept 1 and Adept 3 robots utilize patented direct drive technology to deliver reliable, high-speed performance ideal for a wide variety of packaging tasks. With its compact work envelope and tabletop design, the Adept 604S robot is an economic solution for smaller, light payload jobs. And for packaging applications requiring sanitary washdown procedures, Adept's Pack 1 robot features a hygienic, environmentally sealed design that meets both USDA and European requirements for food handling equipment.
Let us get an explanation of the Adept philosophy in vision-guided robots from our chairman, Brian Carlisle.
Hi, I'm Brian Carlisle, chairman of Adept Technology. You've probably heard a lot about machine vision and know that the term machine vision describes almost any sensory equipment using cameras and analytical software. However, vision requirements vary greatly with the application. At Adept, we believe strongly that one type of vision task, robot guidance vision, is the key to flexible manufacturing. So, we are encouraged by the trend that today, more and more manufacturers are using robot guidance vision in their operations. Adept's vision systems are both reliable and cost-effective. In addition, they are designed specifically for robot guidance. They offer you special capabilities that vision systems for other tasks cannot provide. In this presentation, we plan to show you that robot guidance vision is now practical and can benefit your robot installation.
For truly flexible, efficient manufacturing, what should you look for in a robot guidance vision system? There are three major requirements. First, robot guidance vision must not slow the robot. Rapid data processing is important to maintain cycle times and throughput. Also, the system must handle randomly oriented touching and overlapping parts, because that is how parts are generally found in factories. Finally, it must be easily implemented so your engineering time and costs are minimized. For the first requirement, speed, two Adept Vision features give you rapid processing. The vision electronics in all the Adept systems are housed in the same controller that drives the Adept robots. This way, the vision system and the robot system communicate through the multibus backplane. Most other systems don't communicate to the robot through a backplane and therefore require a separate vision controller. Because of Adept's integrated controller, communication is much faster. Also, Adept Vision has its own dedicated Motorola 68000 microprocessor, so that vision data and robot data are processed in parallel. That means the robot continues its cycle while vision data is being processed. And when the robot reaches its destination, it can respond immediately to the vision information. Adept Vision's integrated communications and parallel processing provide timely information while maintaining rapid cycle times. The second requirement for robot guidance vision is the need to handle randomly oriented touching and overlapping parts. Adept's feature-based recognition technique makes this possible. By feature-based, we mean that it locates the right combination of corners, straight line edges, and arc edges of a part, which it can find at any angle of rotation, even if parts touch or overlap. because as long as enough features are located, the system extrapolates the rest of the image and identifies the parts. This means you can present parts loosely and at any orientation in simple trays or on conveyors. Finally, robot guidance vision must be easy to install and train. Since Adept Vision is integrated into the Adept controller, implementation is simplified because you eliminate the need to design cables and connections for communication between a vision system and a robot with two separate controllers. Write software to communicate between the robot and vision system. Adept robots and vision systems already talk the same Val2 language. And you eliminate the need to write a calibration program to reconcile the coordinates of the vision and robot systems. Training is simple, too. Adept vision systems are designed specifically for robot guidance. They are fast, easy to implement, easy to train, and work reliably on the factory floor. They simplify tooling and preserve the flexibility to handle a variety of parts.
Robot guidance vision is ready and proven for the factory floor. It provides real benefits that give you an attractive return on your investment. These benefits include simplified part presentation, part verification and inspection, and most importantly, truly flexible manufacturing operations. We at Adept welcome the opportunity to evaluate your manufacturing operations to help you determine where machine vision can be effectively applied. Thanks for watching.
While the concept of computer vision inspection might not seem terribly new, the combination of real power and real ease of use definitely is. That's where the Adept approach to vision inspection is finally making a difference between an emerging technology and one that delivers real manufacturing results. Adept Vision AGS and our new VisionWare system is the result of that experience. Combining high-performance vision processing with an intuitive user interface, the Adept system makes vision inspection more cost-effective and easier to implement than ever before. To begin an inspection, parts can be analyzed in either grayscale or binary modes, and images can be acquired from stationary parts or rapidly moving production lines. Once an image is acquired, all the necessary tools for vision analysis are available via simple pull-down menus. Other tools, such as optical character recognition, can be used to verify print quality and automatically track information such as lock codes and serial numbers. And Adept's feature-based recognition tools allow the system to recognize and inspect even randomly oriented parts, making it easier to apply the system in a real-world manufacturing environment.
In the next few minutes, we will show you some of the major application areas for Adept robots and vision systems. The first part will cover the electronic industry. The second, very interesting area of packaging using industrial robots. The last part will give you an impression of the sophisticated area of mechanical assembly and parts handling.
But in today's complex world, the challenges of advanced technology, compounded by competitive world markets, have made robotics a virtual necessity for competitive electronics production. As a world leader in high-performance robot and vision systems, Adept Technology has gained a unique perspective on the use of flexible automation throughout the electronics industry. In this videotape, we'd like to share a first-hand look at how today's leading electronics firms are using today's most advanced robotic systems. Around the world, makers of high-tech electronic products are being challenged to improve quality, increase flexibility, and boost the bottom-line effectiveness of their manufacturing operations. For a growing number of firms, including world leaders in the computer, defense, and telecommunication industries, Adept Technology's flexible robot and vision systems are helping meet this manufacturing challenge. We invite you to join us as we tour state-of-the-art robotic production facilities at Control Data Corporation, Digital Equipment Corporation, and the Xerox Corporation. At Control Data Corporation's Computer Systems Manufacturing Division, just outside Toronto, Canada, this vision-assisted robotic workstation assembles surface-mount circuit boards for CDC's high-end mainframe computers. Designed and built by Gelser Systems Company of Westerville, Ohio, this robotic solution offers greater flexibility than dedicated equipment and provides higher, more consistent quality than manual production techniques. While the robot arm is the most obvious part of the workstation, the system is actually a network of hardware and communications channels driven by custom software run on the powerful Adept controller. This multitasking controller coordinates part feeders and automatic tool changing to allow the robot to locate and acquire over 128 electrically unique surface mount components. To determine which components are needed for a given board design, a CAD-generated database is downloaded to the robot controller. Placement locations for individual components are given relative to fiducial marks on the board artwork. Once these are sighted, the system automatically calculates precise coordinates for hundreds of placement locations. Using this capability, production may be quickly changed from one board type to another without reprogramming or mechanical adjustment. During assembly, an Adept Vision system uses a total of 4 cameras to guide the robot through acquisition, inspection, and placement of over 20 different component types, ranging from very small discretes to the fine-pitch 172 lead quad pack. For this component, fine tolerances dictate an additional visual check of the placement location. Inspection of quad pack leads ensures part integrity while indicating alignment relative to the robot arm. Using this information, the final result for CDC is component placement accuracy within 0.003 of an inch. As surface mount technology spreads throughout the electronics industry, this kind of consistent quality, combined with unprecedented production flexibility, is only one reason innovative firms are choosing Adept solutions for their manufacturing operations. The solution, developed by Digital's Advanced Manufacturing Technology Group and the Shuttleworth Corporation, is a completely flexible, computer-controlled production facility. Here, an entire family of tape and disk drive products are produced by a system of interchangeable manual and robotic workstations. At the robotic workstation, a barcode reader and a grayscale vision system identify incoming components before they're assembled by a 2-robot system. Once the system verifies that all needed parts are available, the assembly process begins. During assembly, the robots use interchangeable end-of-arm tools to perform a wide variety of assembly functions. For instance, one robot uses a special gripper to acquire and position electric motors in the tape drive mechanism, while the other robot uses an automatic screwdriver to complete the assembly operation. Throughout the entire process, the robots are in constant communication with each other to assure efficient, coordinated assembly of 14 total parts. According to Digital, flexible automation has already paid off with the fastest production ramp-up of any storage product in their history. In addition, the Springfield facility has reached a level of quality and production efficiency that makes it competitive on a worldwide basis. As a result of this success, Digital is adding more robots to the Springfield operation and has already chosen Adept solutions for manufacturing applications at other Digital facilities. While the installations of Digital equipment and Control Data show how robotic solutions contribute to new production systems, the experience at Xerox Corporation shows how Adept robots can also work to improve existing manufacturing operations. Here at Xerox's El Segundo, California facility, millions of printed circuit boards are produced each year for the Xerox line of office products. To maintain its competitive position, plant management must constantly find new ways to achieve world-class quality and production efficiency. Recently, it took advantage of two opportunities to improve manufacturing effectiveness with adept robotic solutions.
We've had two systems installed in our facility, a test cell that was installed in April of '86, and that test cell has been an extremely successful system, been in full production, running close to 800 boards per day through it with almost zero problems in the entire cell. The adept robot has performed beautifully for us. In November of this year, we finished the installation and started production in a 3-robot insertion cell. And since that time, that cell has also performed to a high level of productivity for us.
The second installation, also designed by Chad Industries, is a series of 3 robots inserting odd-form components onto partially completed printed circuit assemblies. The first work cell uses a single robot to place connectors and other components with high lead integrity. Parts are acquired from linear and vibratory bowl feeders, and immediately after placement are secured by an integrated lead clinching system. A compliant wrist on the robot's arm confirms a component has been successfully placed. Or when a bent lead or other problem prevents insertion, the robot senses the error, discards the part, and begins the process again. Placement rates for the cell average 12 components per minute and support production of 66 boards per hour, 3 shifts a day if required. Depending on board design, the single cell places up to 14 different component types before sending the board to the dual robot workstation. Both Xerox insertion cells operate using a software package called AIM, developed by Adept to simplify robot implementation and operation. AIM keeps track of feeder locations, component status, and other information required to manage the assembly process.
We purchased the entire robotic system from a systems house, and the systems house modified the AIM software for the features that they added to the cell. And now that we've had that in our shop running, we've also taken the software. We have taught new boards, entered new programs into the system. One of our maintenance operators does that very frequently and finds it very easy to work with and very easy to add new boards and new components to the cell.
In today's competitive market, product packaging is playing a more important role than ever before. Changing package designs, frequent product introductions, and shorter times to market are causing manufacturers worldwide to re-examine their approach to the packaging process. In the past, manufacturers could rely on traditional packaging technologies such as dedicated machinery and manual production techniques. But dedicated equipment cannot always meet today's needs for increased production flexibility. And with higher labor and liability costs, manual alternatives are not always a competitive solution. Now, there is a new choice in packaging technology, an automated solution that actually duplicates the hand-eye coordination of manual operators to replace touch labor in the packaging process. The choice is flexible automation from Adept Technology. Join us now as we look at Adept packaging solutions for case packing, candy, convenience food, bakery, and meat handling operations. For case packing applications, the Adept solution provides manufacturers with an unprecedented level of process flexibility. Using Adept robot systems, staged product can be gently packed in a wide range of configurations with reliable speed and precision. And with the addition of Adept Vision for product identification and tracking, the system can easily handle even a randomly spaced product flow. For producers of fancy candies, the Adept approach provides a high-speed yet delicate packaging solution that locates, inspects, and places candies on a moving line. Adept Vision allows each system to recognize a candy's shape and position, while the line tracking capabilities of the Adept controller ensure precise candy placement. And since system changes are made in software, the entire line can be converted from one assortment to the next in minutes. For increased production rates, Adept robots can be equipped with multiple pick grippers. And with powerful automation controls, Adept systems can link asynchronous processes by accumulating product when the downstream process is stopped and reintroducing it when production allows. In the convenience food industry, many production operations also require product assembly. In this application, Adept systems recognize component locations and assemble product directly on a moving line. Since Adept systems are completely programmable, many assembly options are possible, including the placement of individual portions into serving trays. Bakery applications for Adept robot systems include picking product from an oven conveyor and assembling complex package arrangements.
In our first presentation of a flexible manufacturing robot cell, an Adept 3 robot assembles two different products in one work cell. All parts needed are transported into the cell via conveyor, which is connected to a flexible palletizing system. Using the gripper, the robot assembles a sub-assembly for a vacuum cleaner. The assembly of the second part begins. Nasal sprays come in large varieties. These ones are assembled in this flexible, vision-guided robotic work cell. An Adept 1 robot with an integrated vision system using 4 cameras and a sophisticated multifunctional gripper assembles and tests one nasal spray consisting of 6 parts within 10 seconds. A high level of flexibility is achieved through the use of a vision system to guide the robot to the location of the parts. The part feeders are capable of handling a large variety of different sizes without any mechanical adjustment. Using an Adept 1 robot with a multifunctional gripper, the rollers are assembled to the underbody of a vacuum cleaner. The Adept 1 robot is able to handle all parts necessary in this work cell. Adept Technology would like to thank you for your attention.
Approach, vision and control are designed out of modular software units that operate on common workstations at real-time rates. Feedback from 2 cameras is provided by visually tracking the robot end effector and a target object. For the experiments shown here, we are tracking 24 line segments across 2 images at 20 Hz on a single Spark 2 workstation equipped with a digitizer board. Specially designed image-based regulators support a variety of positioning modes. including 3 degree of freedom point positioning, 4 degree of freedom collinearity constraints, and full 6 degree of freedom relative positioning. The accuracy of these methods is on the order of a millimeter in depth. One advantage of these methods is that their accuracy is not sensitive to calibration, as shown here when we move one of the observing cameras while the system is in operation. By reconfiguring the tracking slightly, the same feedback methods can be used to place a screwdriver on the head of a screw. Using a 4 degree of freedom collinearity primitive, the screwdriver is first aligned with the screw. We then superimpose a motion along the alignment axis to move the screwdriver downward until contact. For reference, the head of the screw is 6 millimeters in diameter. Similarly, tracking and control are easily reconfigured to insert a floppy disk into a disk drive. This utilizes a 5 degree of freedom regulator composed from a 3 degree of freedom positioning primitive and a 2 degree of freedom alignment primitive. Future research will be devoted to handling visual occlusion, vision-based planning, hybrid feedback using vision, and vision-based programming environments.
We have developed the Hanetsuki robot. Hanetsuki is a traditional Japanese badminton, and here we think of a task to return an incoming ball with a racket. The immobile robot has to return a ball to the human opponent with a racket. The system uses 2 perpendicularly fixed cameras, camera B and camera A, to attain the trajectory of the ball. And this red ring is a nearby area of a target where the ball must return. 5 degree of freedom robot and parallel processing board is used in this system. This scene shows robot practicing to hit the ball. The aim of this task is to return any kind of ball to the target. We employ learning algorithm to sophisticate the action commands. The learning algorithm used in this system consists of updating and smoothing action commands. By implementing this algorithm, we could compensate for the insufficiency in a model-based approach. As a result, the robot could play Hanetsuki with human. There is no other robot that could perform Hanetsuki task as good as this robot.
This experiment is an example of dynamic skill in which the inertia of the object is utilized for manipulation. After the object is released from the paddle surface, it is supported by the contact edge. The rotation of the object and the motion of the edge are dynamically coupled through the inertia of the object. The edge is considered as a passive joint, and the object rotation is controlled by using this coupling. We plan the trajectory of the arm based on a dynamic model of the object, and the trajectory is simply executed in an open loop. Such dynamic skills will enable a wider variety of manipulation tasks compared to conventional kinematic skills. In addition, some tasks can be accomplished faster, and heavier or larger objects can be manipulated by this approach.
We have developed a prototype robotic work cell that integrates online planning and real-time control. This work cell can perform complex multi-step tasks autonomously. Typical applications of this work include rapid deployment assembly workstations with flexible part feeding. In this simulated environment, the pink represents goal locations and the black obstacles for the parts. Parts are fed in random order at any time. The obstacle and goal locations can be changed online, and the changes will be reflected in the subsequent paths. In this experiment, 2 manipulators are used to perform several operations, including dual-arm object captures from a moving conveyor, motion among obstacles, rig grasps, and handovers. A unique feature of this system is that the different subsystem modules, such as the planner, robot controller, and graphical user interface, are distributed among different computers and communicate through a local area network. The desired goals are indicated by the color paper on the table. All objects are tracked by an overhead vision system. When a new part appears on the conveyor, the planner is notified and generates a capture trajectory in fractions of a second. The robot control subsystem follows the trajectory until the arm is close to the part. The final intercept maneuver is performed by the robot control system autonomously under direct vision feedback. The planner generates capture trajectories using the object velocity estimated by the vision system. The initial overshoot in capturing the golden part illustrates that an inaccurate initial estimation can be corrected during the final intercept maneuver. Once an object has been acquired, a delivered trajectory is generated by treating all objects on the table as obstacles. Note the regress operation caused by the shoulder joint reaching its limit. The planner is aware of the kinematic limits of the arms and will plan regrasp operations whenever a change of hardness is required. By relieving the work cell programmer from specifying all the maneuvers ahead of time, the work presented here can reduce the time required to set up a manufacturing work cell.
This video demonstrates how control primitives can be sequenced to address a variety of geometric and kinematic task constraints. All the demonstrations included in this segment are generated by activating 3 controllers. One generates a collision-free trajectory in configuration space, another coordinates multiple contacts on C-space boundaries, and a third regulates the posture of multi-manipulator systems. These feedback controllers are bound to degrees of freedom in a control gate. Our conjecture is that such control structures can be somewhat device-independent, combinatorically tractable, and robust. Here, a control gate composes these controllers to stabilize and rotate a task frame at the center of the spherical geometry. Precisely the same control gate exploits the kinematics of the Utah MIT hand in a different fashion, yielding a new geometric gate to rotate a cylindrical object. By attaching the task reference frame to the robot rather than the object, the same control sequence can be used to stabilize the robot as it interacts with a planar geometry. Using the same controllers, a walking gate can be constructed to translate the task frame while maintaining stability. We are developing techniques that permit responsive, distributed control architectures to scale to complex systems and more general tasks. These examples illustrate one way in which a control basis can enhance robustness with respect to geometry and manipulator kinematics. Preliminary results suggest that this control structure dramatically improves the combinatorics of planning and learning in this domain.
Robot 2 is a hexapod with 3 degrees of freedom per leg. Each joint is driven by a 6-watt DC motor, and a potentiometer is used to measure joint position. Proportional feedback position control is applied to each joint, wherein both the position set point and active stiffness are controlled by the locomotion controller. Strain gauges measure the axial load in the most distal segment of each leg. Active compliance distributes the load more evenly among the legs as the robot attempts to maintain a stationary position but must react to external disturbances of the feet. In the case of a relatively small lateral foot perturbation, the robot complies. This is achieved by reducing the gain in the proportional feedback law. If the perturbation is sufficiently large, however, the leg responds with a stepping reflex, wherein the foot is repositioned to better support the body. Searching behavior, which has been documented for locust walking on irregular terrain, is included to help locate a foothold in case one is not found. The mechanisms thought to be responsible for the leg coordination of the walking stick insect were expanded to produce general walking on a plane, then used to coordinate the legs of Robot 2. The robot walks in a continuum of gaits, from the slow wave gait, where one leg steps at a time, to the fast tripod gait, where the middle leg on one side of the body steps in unison with the front and back leg on the other side of the body. The generalization of the stick insect mechanisms allows the robot to perform turning and crabbing gaits, as well as forward and backward walking, all without discrete gait transitions. The gaits are not pre-programmed, but instead result from the dynamic interactions of the individual leg controllers in response to forward, lateral, and yaw velocity inputs. This experiment, which has been previously performed on the stick insect with similar results, demonstrates how a detained leg can continue to support the body while the other legs maintain a